Hi, everyone. Thanks for joining us. Today, our presentation is titled Designing Wafer-Level Chip-Scale Packaging. I'm Carmina. Matt, you now have the floor.
Thank you, Carmina. So today's topic, thanks for everyone for coming. And this is the second webcast in a month. So this one's about designing wafer-level chip-scale packaging. And I have a lot of great content for you today. Actually, I'm hoping, just like the last, if anyone was at my last webcast on stability, I like to spend most of my time just showing you how the things work in the tools and the design tools. So I'm going to try to do that today. There's a whole bunch of material, but I'd like to try to spend about half an hour on the slides if I can, and then move on to some live demos. I'll be doing everything live, so if I mess up, sorry. So first, we're just going to talk a little bit about wafer level packaging, some of the advantages and challenges of it. We'll just give a little bit of a review. I'm assuming that if most people are on a webinar about designing, that they have at least some idea of what wafer level packaging is. Then I wanted to give you two examples that are pretty interesting. One's a Keysight internal hardware example, and the other one is a GLOBALFOUNDRIES 80K integrated phased array on a package. We'll talk about a couple of the challenges, and we're really going to zero in on one of the challenges, which is about designing the wafer level package. Okay, so I wanted to start out with just some technology trends. And there's two high-level trends that I really like to highlight here. What's really interesting to me, I mean, I've been around the industry for a little while, and it used to be if you're working on, aerospace and defense, you have one set of technology. If you're working on, commercial cellular, you have another set of technology that you're working on. And what I'm really seeing nowadays is everything's sort of converging because a lot of the standards are moving to higher frequencies. That's, of course, driven by data and bandwidth. And there's also more complex systems at the same time. And this is kind of happening across the board everywhere you look. So my favorite example is probably I don't think I'm that old, but I don't think my car is that old. But I can remember the last car I had and that I just got rid of. The highest frequency piece of hardware on that car was the FM radio. So that went up to about 108 megahertz or so. And then if you compare it now to most cars that you buy, automobiles, they've got at least some millimeter wave radar. Some of them have quite advanced millimeter wave radar systems. That's up at like 77 gigahertz. So if you think about the difference in complexity, first of all, the higher frequency, that's a pretty big difference in frequency between 108 megahertz and 77 gigahertz. But also just the complexity of the system. FM radio versus a millimeter wave, parking assist or a self-driving vehicle. That's just a huge amount of complexity there. And so that's going to be kind of a recurring theme here when we think about why we're going to wafer scale packages. And I've got more examples if you're working in the commercial cellular space. If you look at the different generations of mobile technology, the frequencies increased pretty modestly. So as we went from 2 to 3 to 4G, we got about a 1.4x increase in 17 years. Well, when we go from 4G to 5G standards, there's about a 12-year gap between the rollout of 4G and some might argue the rollout of 5G. Well, for that, frequencies are increasing by 38x in 12 years. That's a huge increase in frequency for such a thing. We can also look at aerospace and defense. If we want to look at complex systems, some of these aerospace and defense things, we're talking about systems of systems, and the complexity is just growing in orders of magnitude. So a lot of folks in that industry are turning to these heterogeneous integration to make that sort of thing happen. So there's a lot of stuff going on across the industry. This is one of my favorite quotes. This is from a 5G design manager. And he says, we used to consider packages as a painful way to go from the IC to the PCB. But with millimeter waves, it's now an integral part of our design cycle. And it opens possibilities we've dreamt of years ago. And that's really kind of the theme here. Packages are, they offer so much potential, but you really have to be able to master the design of these packages a lot differently. They're no longer an interface to move off of your PCB. They're actually becoming a part of your chip design more. So I wanted to dive into that a little bit as we're starting here. So 5G, why is 5G, what's behind this quote, right? Why is 5G a game changer for packages? Well, higher frequencies and bandwidth. So I've got a whole bunch of data here, but on the top left-hand side, these are the frequency bands. So 5G extends over a huge frequency band. And, down at the lower frequencies, I think the technology mixes are relatively the same as the previous generations for the most part. There's still more complexity. But you also notice on the right, we're going up to 28, 39, up to 76 gigahertz, and there's some plans being investigated for future releases going up to 90 gigahertz. And you couple that with the incredible amount of bandwidth that you have for these things, 10 or 20 gigabytes, and really low error vector magnitude requirements. And what that really boils, if I was to say, like, what's the one thing that the result of that, it's that the interconnect just becomes so critical. Everything really matters at that, because any kind of parasitic inductance that you've got going on when you're talking about these kinds of frequencies, these kinds of data rates, it becomes the bottleneck all of a sudden for your bandwidth. So it can be a huge challenge to develop this. Here's another aspect to it. As frequency increases and all these things are happening, antennas really become a lot more of part of the circuit design than they have been in the past. You think about a 3G phone or something, you had an antenna, you plugged it in, it was part of the phone, maybe it was in the case. So what's happening? Well, frequency goes up, and we all know that the atmosphere gets a lot more lossy as the frequency goes up. So the propagation loss goes up, the interconnect attenuation and delay go up quite a bit as well. The good news for designers is that the antenna size, of course, decreases. And so we can use phased arrays. They become viable all of a sudden in some of these cellular applications to overcome the losses and also to improve the spatial efficiency. And I've got on the bottom left-hand side here a plot of the patch antenna width versus frequency. So of course, if you're below, say, if you're at a gigahertz or two, well, it's not really tenable. The antenna size is so much larger than your package. But as you come into the 20 gigahertz to 30 gigahertz range, they start to become on the order of your package. And when you get much above that, by the time you get to 50 or 60 gigahertz, these things are below a millimeter per antenna on your patch. And that means that you can put phased arrays directly into your packages. So this is just one example. If you searched IEEE, you'd find so much literature about people using wafer level packages to integrate antenna arrays into there. This one I brought up because I thought it was kind of interesting, as a former antenna designer. The dipole, this one uses dipoles and patches. So dipoles come down just the same way as patches. And in this particular paper, they were using a set of patches. They packaged it with a CMOS RFIC, but they also used dipoles to control some of the lateral stuff. So, I think we forget about that, but dipoles come down in size quite a bit too. And so that's why I thought that I highlighted this paper. I thought it was kind of interesting. When we're looking at the antenna patterns on the bottom right-hand side, if you have an error introduced, a phase error, which can of course happen because of the interconnect delay, or an amplitude error that can happen because of some of the antenna attenuation or the loss, we can have these side lobes pop up on the phased array antenna pattern. And that essentially is going to radiate energy into a direction that we don't want it to radiate in. So it's going to lose efficiency. So that means it's really critical to be able to design the chip, really the circuits, and the antennas together at the same time. And again, if you go back to 3G or 4G and you think about designing, I've designed a lot of commercial cellular power amplifiers myself. You could design the amplifier and you connect it to a 50 ohm load. And of course, you characterize it over some VisWAR for an antenna. But you take an antenna and you connect that one antenna to your one part. But for 5G, it's completely different. If you're talking about phased arrays, you have all of the circuits are driving the antennas, and all of that complexity is what's contributing to this overall beam that you're trying to create in the antenna pattern. So it's a much bigger challenge to deal with. Okay, so now I'm going to do a brief overview of wafer level packaging. This could be a much longer seminar, and I could talk about wafer level packaging for a lot longer than this. I'm only going to have time to do just a brief overview of it. There's certainly more information available. So let's talk about what is wafer level packaging. Well, wafer level packaging is where we perform the packaging steps at the wafer level, like it implies, rather than on individual chips. And so for normal process flows without wafer level packaging, we take the chip, we dice it up, we put it in some package and do something else. Well, for wafer level packaging, we're going to do that more at the wafer level before it comes out of the fab usually. And there's a lot of different types of similar packages. The ones I'm going to talk about today are really just fan-in and fan-out packages. That's not to imply that these are the only types of wafer level packages out there, but these are the ones that I'll just briefly cover here. So the two types are fan-in and fan-out, and I've got some graphics here. So fan-in wafer level package, this is done directly on the wafer before the reticle is diced. So we don't even dice the reticle yet. Instead, what we do is apply a redistribution technology and then an underbump metal, and then we put solder balls on top. So essentially, we take those really small bond pads on the chip and we route them to solder balls, which we can later flip onto a package. So this is done on wafer before the reticle is diced. Pretty straightforward, this one. Now let's talk about fan-out wafer level packaging. So on fan-out wafer level packaging, it's a little bit different. First, the wafer gets diced, and then it gets placed onto a carrier wafer. And this undergoes molding and redistribution. So essentially, we're able to spread the chips out a little bit more, and then we can put some mold compound around the outside of it and apply more redistribution technology, a bigger redistribution, really, and more solder balls, so we can make the wafer or the package size a little bit bigger than the chip. So the key difference here is that if you look at a wafer level package and you see that it's bigger than the chip that it's on, I'll show you one example from Keysight later. You can tell that it's a fan-out wafer level package. Okay, so but the other thing I want to mention in my example, I'll show you this, is it's possible to actually do both fan-in and fan-out wafer level package. So let's talk about the pros of fan-in wafer level package versus fan. I mean, everyone, there's always this question, well, which one's the best one to use? And of course, just like anything else, it depends on the application that you're working in. Fan-in wafer level packaging, obviously the die size footprint is smaller, so you can make a more compact package. It's an easier design flow, and you can just apply it to the uncut wafer. You don't need to repackage it onto this or replace it onto this carrier wafer. Fan-out wafer level packaging, the pros, obviously more I/O. So for fan-in wafer level packaging, you're talking, I mean, for 8x8, you're going to get maybe 500. For fan-out, you can achieve a lot more I/Os there. Potentially have more redistribution layers. I mean, typically for fan-in, the redistribution is pretty minimal. And you can get PC grade reliability because of that, the molding compound and the RDL layers. And you can also use known good die. I mean, if you're going to do a packaging step like this, you can select known good die, because if you're going to take a wafer and you have, say, 90% yield on your wafer, when you're packaging that, the additional packaging steps you're doing on the chips that aren't working or fail the yield process, that's just a waste. That's lost gross margin, lost revenue, really. So with fan-out, you can pick the chips that you want and the good chips, and then you can only package those. That's a bit of an advantage. Okay, so that was a really brief summary. I know that, and there's a lot more that we could talk about in there. So there's certainly different types of technology, and there's a lot behind those little blurbs that I showed. Just to summarize here, what are some advantages and challenges? Well, the advantage is that you get high frequency electrical performance at lower cost. It's pretty clear that you can. This is a high performance, low cost kind of thing potentially, and it enables really high levels of integration, because you can do this on multiple chips. You can integrate things together very tightly. It certainly simplifies manufacturing and test. You can do that all now potentially at the foundry as opposed to in some other assembly setting. So that makes it easier. There are some challenges. The first challenge is fine pitch interconnect limits design flexibility. But the way I think about that, I mean, I consider myself a microwave designer. So when I design, I feel comfortable designing 50 ohm transmission lines and nice thick metals and all part of it. And when I look at chips and I look at interconnects, like you'll see on wafer level packaging, these start to look what I would consider parasitics. And so so you don't have all these nice ability to create these really well controlled lines, and when you get to high frequencies, you have to kind of think about that a little bit more. The other thing is post-production lab tuning is pretty limited. That means you've got to get it right in the design. I mean, I've done on boards and laminate types of packages. I've taken little X-Acto knives and I've shaved traces or cut traces, inserted components. I've even on chips, I've taken diamond scribes, brushed down inductors to make to get rid of a big inductance to fix a stability problem or something. But when you have everything packaged up on the wafer, you're not going to be able to go in and start hacking away at your design. And it's really important, it's going to take more time in the design phase to get it right. And the third challenge, this is actually going to be something that I focus on in my demos. We're going to talk about this, which it's complexities in assembly and EM analysis. So these last two go together. If you don't have limited tuning, you have to get this right in the design. At the same time, it's really hard to do the design right now, given the current state of the design flows. It's really difficult to assemble technologies, and getting the EM analysis done is challenging in the design process, because a lot of these flows, I'm going to talk about that later, but a lot of the design flows are really built for more of verification. Like you design the whole thing and you EM the whole thing and you figure out if your design's working or not. But when you're designing an interconnect, it's not so easy to just take it to the electromagnetic state. Okay, so let's move on to some wafer level packaging examples. I just want to give you two really practical examples that I'm pretty familiar with of wafer level packaging and talk about some of the challenges and some of the possibilities. We can look at these as representative examples. And the first one is kind of fun because this is actually something that's in one of our Keysight instruments. This is our UXR. It goes up to 33 gigahertz. And so inside of that, there's wafer level packages. So on the left-hand side, what I have is the older style package that we've used at Keysight. So this is a traditional hybrid front end. This uses thin film interconnects. We're using aluminum nitride shins, thin film routing, mesh wrap interconnects. So, and by the way, we're also doing internal assembly and test on that. And when you look at that, I mean, it's, again, as a microwave designer, it makes me pretty comfortable to see that, because I think I can control all the pieces. And for example, if one of the traces isn't right or one of the interconnects isn't right, I can fix it. I can go in and swap out another thin film, or something else, and I can change the substrates and bonding. The problem with it is it's really expensive. And so what we were able to do, or Keysight Labs was able to do, and it's the sources on the bottom right. This is based on a paper that Keysight's published, but was able to reduce the cost of this by 60%. While actually not only maintaining the same performance, but in some cases even getting better performance with wafer level packaging. So that's what I'm showing on the middle picture there. It's we do this wafer level package signal conditioning ICs, SIGI, and we do PCB routing, SMD assembly, and interconnect. And instead of testing it internally, now we're able to do the assembly and test externally with improved yields. And the one area of cost that I think probably sticks out to you is the shielding. I mean, if you look at this, if you look at the left-hand side package, there's a big hunk of metal on there, and of course there's less metal on the right-hand side. So that kind of speaks to one of the advantages when you're able to contain all of your traces into your interconnect and circuits into a smaller package. That means the signal is not going to radiate out as much, especially when you get to higher frequencies. You think about, I showed you earlier, some of the antenna sizes, when you get up into the gigahertz, start to become on the order of the package. Well, if you look on the left-hand side, all of those connections going off of the chip, the interconnect is radiating as well. And so we have to shield it better, whereas in the middle, we don't need to shield it. And on the bottom, I have actually got a picture of the chip. So I think I should have made this a poll question, but this is, of course, fan-out wafer level packaging. And the reason is because you can see the chip, and then you can see that the package is bigger than the fan-out. I wanted to dive in a little bit more because this is a group that we work with pretty closely, and talk about some of the learnings that came out of this work. And so how can you get better improvement by going to a package like this? Well, here's two really fairly straightforward examples. The first one is you can improve the transmission of your interconnects. So one of the things that Keysight was able to do in this process was reduce the pad size, because we no longer had to bond. So when you have to bond from your package to your chip, you need a certain pad size to be able to handle the bond landing. But in this case, we can now just flip it over and we have a ball. And so this is a simulation, an EM simulation of the dipad parasitics bond versus ball. So you can see at low frequencies, a couple of gigahertz, it really doesn't matter at all. Like down at commercial cellular frequencies, there's very little difference. When you get up into the gigahertz range, and I'd argue some of the new 5G millimeter wave frequencies, right? There's a huge difference now in insertion loss. It's much better to have a transition like a ball bump rather than a bond wire, and that's just the pad. We can also talk on the bottom now about the wire. The wire is also a pretty major source of loss and disconnect and step response. So the insertion losses is of a trace, and this is showing a bond wire with a couple of different loop heights on one of our packages. And you can see that the bond wire is going to have tremendous amounts of loss. Now you could parallel these up and get a little bit better, but still the point is if you can just keep a straight trace going through, you're going to get quite a a bit of insertion loss back from your design. So these are the types of things that you can do when you've got wafer level packaging available. One other area that I want to highlight from this work, this is actually the RDL technology that I'm showing on the right-hand side for this chip. And you can improve isolation. And I think I alluded to that in the earlier slide. But one of the things that was done on this design is kind of made a fence around the analog and digital sections. And it was a ground fence, so you can make fences with solder balls. And also looked at the isolation I'm showing is you can increase the population of ground balls. So just because you have a pad that's not being used, you can ground that pad, and you can actually improve the isolation quite a bit. So I think on the bottom we were showing 14 dB of improvement by just populating 2 strategic ground balls under the RF section. And you can figure out which ones are important by having a good simulation and flow. Okay, so we're going to switch gears now to a different example. This is a phased array, a wafer level package. This is the antenna co-integration that I was talking about for phased arrays. So this is the design done by GLOBALFOUNDRIES. I think I've got 55 gigahertz here. We've got some simulation and measured data there, but I think it's actually more like 60 gigahertz. This is a Y-gig phased array, and you can see the structure of the package. So in this case, we take this SiGe chip. So by the way, this is the GLOBALFOUNDRIES 22 nanometer FDSOI technology. This is the application development kit, and we're assembling that. We're putting that in a fan-out wafer level package, and then on top of that, an antenna module is going. And so this is just showing some of the complexity on the bottom here. We've got the IC. So on the bottom, you can see the fan-out. That's the little purple part. I don't know if I have a pointer here to show you, but and then we've got a via that's actually extending out of the fan-out wafer level package. So the package is going down to the board, but also up to the antenna. And then the antenna, we've got a feed and the patch antenna on the top. And out of that whole thing, what do designers need to get? They need to get the entire radiated pattern here. So not just designing the circuits anymore, but seeing the far field at these high frequencies and being able to steer the beams, which is really a pretty big challenge. So along the lines of challenges, I just wanted to use this as an example to talk about how can we close the gap on some of the issues that take place in this type of design flow. So in other words, what do we need? How can you pull something like this off and get it right when you can't really do much tuning in the lab for something like this? Well, the first thing you need to be able to do is technology assembly. So in this case, what we've got to do is take this 22 FDX IC from GLOBALFOUNDRIES. It's a fully depleted SOI chip, right? And we have to flip it essentially flip it onto our wafer level package. So we've got a wafer level package technology that's a separate technology file, sets of layers, substrate, all of those things, and we somehow have to merge those two substrates together. Then we've got to take the other package, which is that's actually on the far left. This is the L2 package. That's the phased array, and we've got to stack that on top of the combination of those first two packages. And then we've got to take those 3 packages, that stacked set of 3 packages, and put it onto a PCB. And then that's what we're actually going to take to the second challenge in the design process, which is electromagnetic simulation. So we've got to take that thing and then efficiently get electromagnetic results out of that, which is a really big challenge, because if you consider the geometries involved, you're going from very, very small geometries on the chip to quite larger, and could even get larger on the board geometries of the phased array. And then underneath, if you've got the board, that's going to be even bigger geometries. So there's all the traditional things. Of course, we can try to characterize the package. So you need to be able to look at all the packaging stuff as it is. But also, one of the challenges, if you're thinking about the circuit design itself, if you're going to co-design the circuit in the package, what I'm showing here on the top is we always think about simulating the entire phased array all at once, the whole thing. That's what gets, if you read the IEEE papers, that's what you see people showing. It's this whole phased array. But to really get there, you have to be able to do part of it while you're designing. And so this is just showing a couple of the antennas on the left-hand and right-hand side. On the top here, we're only looking at those antennas now, and we want to figure out how well matched are those in terms of phase. Are we getting a similar response across there? Because if you have small differences between these antennas, that can really affect those side lobes in your antenna patterns. And then on the bottom, we're also talking about potentially current density, so power integrity types of problems, where is too much current going through these really small vias, and also really looking at how the circuit is performing. So we have all of these feed networks are going to come together. It's sort of a rat race combiner with all these different antennas, and it's very challenging. So there's a lot of electromagnetic challenges, and that has to happen on the circuit design. That's not something you can assemble once. You're going to expect to do this probably 50, 100 times during the design process at different stages. So I wanted to zero in for the rest of my talk about what are some of these technology assembly challenges, and what are some of the EM challenges that we're going to run into. And these are the things I want to show you in the design tools, rather than just, I think having a whole webcast if I was just showing slides would be boring. So I'm going to try to show you these things in action. This example I've got in our tool, Advanced Design System. This is a combination of, earlier I said you can combine fan-in and fan-out packages. So this example has that. We've got a silicon transceiver that's in the middle, and we're actually going to do fan-in packaging on that. And then we're going to mount that onto a fan-out package. And one of the things you can do is you can put other chips in. So we're going to put a filter chip in there on the fan-out package and connect everything together. And so the goals are going to be, we want to put these chips all together. And by the way, there could be 5 different or 20 different versions of the transceiver. And so we want to be able to track that. As we're assembling all these things, we want to be able to track that, co-design the interconnects and the system blocks, and incorporate the results into a full assembly simulation here. So I'm going to talk about 2 different capabilities that we worked on. So at Keysight, I think one of the things, the advantages we have in being both a company that develops hardware, develops chips, develops wafer level packages, develops pretty complex boards as well for our instrumentation products. We also develop the design software. We interact a lot. And so one of the solutions we came up with is really based on a lot of the feedback and the interaction we get with some of the hardware folks. So I put some words up here: simple, powerful, versatile, and scalable. These aren't just like words that I came up with. These are actually the specs that we have. These relate to some of the specs that we had when we were building this assembly capability into our tools. These were the specs. So instead of talking about these too much, I'm just going to show you how they work in a minute when I share my screen. Before I get to that, I wanted to also talk about the second part of this EM simulation challenges. And I think the biggest challenge, if you look at a high level, the biggest challenge is that the EM simulations aren't typically set up to be part of the circuit design process. Like normally you're going in, you're designing your circuit, you're doing interstage matching at the chip level. Maybe you're doing EM simulation on a chip, but when that thing goes off into the package, that's another design flow, and that's going to be, the chip is complete. Now we put it in the package, right? Now we design the package, now we EM the whole package. Now that's complete. Now we put it on a board. What I'm saying is, as we move to wafer level packaging, that changes. That's not the case anymore. When you design the chip now, you've got to also design all of that package potentially out to the board. I mean, that's one of the things we're seeing internally, is that, with these chips, if we want to get the performance, we have to go all the way out to the board at the higher frequencies. So there's all these pieces of the EM that are difficult. And on the solver side too, I'm a circuit designer. That's my background. I don't have a PhD in advanced meshing algorithms, although some of my colleagues do here. But I don't want to have to know about all of these things. I want to get a good result, and that's a real challenge if you're a circuit designer. What things do you put into the simulator to get a good result? And probably the biggest, so we've got port configuration, meshing. These are all challenges. And then the solver itself is oftentimes tied to one tool, right? So it's too rigid. But if you consider assembly, we have to actually sort of compile information from multiple different types of tools. And we have to be able to take, the same type of solver and be able to apply it potentially to a chip, to a module, and all the way up to maybe a package or a board. So that's what I was going to talk about a little bit today. I think what I'm going to do is try to share my screen here. Before I get to that, I just want to give you the answer first. The RF Pro tool in ADS is something that we've developed to help resolve or solve that problem for design engineers. And the difference with RF Pro versus older EM simulation technologies is it's really about analyzing signal paths. So if you think about the way the package, the thing I'm going to show you today, we have a silicon chip, we're going to go through a redistribution, we're going to go through a packaging, we're going to go through a bond wire onto a gas IC. that's just an interconnect. So that traverses 4 or 5 technologies, yes, but really what I care about is the interconnect through all that technology, and it's tracing that response, because all of those pieces need to be co-designed together to get this thing to work. If I don't design the RDL layer well, it doesn't matter if I have a really nice interconnect on my package. The RDL and the package routing are going to have a discontinuity, and that's going to be a problem at higher frequencies. Okay, so with that, I think what I'll do is share my screen here. So what I've got, first I'm just going to talk about the assembly, because there's a lot of subtle details in the assembly. Before I jump to the bigger example, I just wanted to sort of point out a few things. So I have 2 different libraries here. The first one, this is a redistribution technology. So basically I've got my silicon chip here. I'll show you the substrate. I just have my IC here. So I've got a silicon substrate. I've got my routing layer, and then I've got an under bump metal and a bump. So this is a very simplified version of the real chip I'm going to show you is more complicated, of course. So what I want to do is take this thing, and these are solder bumps here, yeah, or micro bumps, and I want to instantiate this onto a package. So I'm going to bounce over here. Now this package technology is completely different. I mean, here's this is more like a board technology, or maybe a BT type of package. So I've got multiple layers here, routing layers, conductors, all those things. And I think the main point is, if you look over here at the layers on the left-hand side, these are all completely different layers than the other technology. And not only that, I mean, if I take a ruler here, I'll put a ruler on, I'm just going to make some measurement. The thing I want to show you is, hopefully you can see that, this is in microns. So this technology is in microns for the chip. That's expected. Most chips are in microns, at least in their design kits. And if I take a ruler here, let me put it on a red layer so you can see it. I'm going to make some measurements, and the point is, this is in mils. So these databases have different units, different layers. Under normal circumstances, if I took this thing and tried to instantiate it, like I might on a chip design, right? I have maybe I have some kind of bandgap reference or something, and I have that piece, and that's a piece of hierarchy, and I instantiate that into my larger circuit. That's not going to work here, because these things are just different technologies. So what I can do, just talking about that word simple that I used at the beginning, I can go to options technology, and I can go to nested technology here, make sure I'm in the right library, and I can apply this thing called smart mount. And I've got a couple different settings, not too many. So we have bottom mount, flip chip. Bottom mount is, I'll show you what those are. I can do a custom mount, or I can do what's called a multi-mount. That means I can decide when I place the component, whether or not I want it to be flip chip or bottom mount. And there's a couple layer mapping. The thing to know for now is, I'll show you this stuff, is I'm just going to stack them. I'm basically going to just put the chip on top of the board and see what happens. And then we'll talk about some of the implications of doing that. So I'm going to say apply there. And I'm going to go back to my other library, and I will instantiate. This is just like any other piece of hierarchy in an IC design tool. So I'm going to take this is called bumps, and I'm going to instantiate it. Now, when I do that, it's going to ask me, do you want this to be a bottom mount or flip chip or other? So let me just pick bottom mount. And now when I put this thing in there, I can instantiate it like any other cell. And you can see what happens. What it really does is it stacks the backside of this chip, that's the bottom layer of the chip substrate, on top of the metal layer, and the bumps are appearing there. Now I can mount this. I can change this layer. So I can decide, you know what, I actually don't want to mount it on the front, I mount it on the back. And it automatically flips over to the backside. And let me put it back to the front. So I can mount this front or back, even inner layers for some more advanced packaging. I can also change the mount subtype. So I can say, you know what, I don't want a bottom mount. I actually want to flip it over. And you can see that it flips over here. And what do we have? We have the bump metal, that interface, and then we have that stacking directly on top of the package, the sort of board or package level metal. Okay. By the way, I'm using, this is ADS 2021 update 1, so it hasn't been released yet. I think this is kind of fun to use because it's basically my first time using it. So one thing I want to, at least with this is my first time doing the whole demo with ADS 2021, so we're kind of flying by the seat of our pants here. Let's see how well it works. I'm going to show you some new features in the tool too. One of the things that is a challenge, I mean, let's say I'm going to put this onto some traces. I want to make connections to it. Normally, if you drop a chip like this onto a package, you want to have metallization on the package. You need landing pads, of course, for the solder balls to connect to. So something like this really isn't going to work for that case. What I'm saying is I'd really want to take like a circle here. And I'd want to have some kind of a land pad there. That way, I don't want to toggle too much between 2D and 3D, but I want something for this chip to land on. Otherwise, that's not going to work. So it may be complicated. I mean, a lot of times if you're designing a packaging technology, if you're starting to assemble pieces of a packaging technology, you have a chip, you're building a package, you don't have all these land pads really vetted out yet. I mean, you have to have your complete chip a lot of times before you build the land pads. So let's see if we can start with that. So we talked about simple. Now let's talk about how powerful we can be with this capability. So I'm just going to go back to my bumps here, and I'm going to change one option. I'm going to go Options, Technology, Nested Technology. Now, before I stacked these on top of one another, but in this case, I'm going to change it. I'm actually going to say Map Layer and Aligned. And what that's going to do is that's going to take this chip with the bumps and everything, and it's going to take this layer as an interface layer. Now, remember, I can configure this. This is in my substrate. And it's going to create, when I mount this, it's going to merge this into the landing technology and create the layer that I mounted on underneath. In other words, this chip is going to essentially create its own pads on the fly. So I'm going to say flip chip here, and put it down. And when I do that, if you see here, you can see that now I didn't draw this circle in all of these pads. So the pads are created in the parent technology by the chip itself. So I'm creating layers on the fly as I mount this. So that's what I mean by powerful. Here's another example. This is just a completely different chip. So I've got different pads, different locations. That happens a lot when you're first doing the design, right? Well, these smaller pads, they'll still create their own metal in the technology that you're placing them into. Okay, well, even so, that still may not be good enough. If you're doing a package design, I mean, one example, so we've got a pad now, and it's the same landing as the solder ball. But when the solder ball goes on a package, in a lot of cases, I'd actually want it to be bigger. Because usually if the landing is exactly the same size of a solder ball, you're going to have placement errors, problems like that. This is probably more like what I'd want to have, a larger metal to land on. And the other thing with some of these technologies, in this case, I've got a solder mask layer. So there's actually, on this package, an isolation protect layer on top. And technically, what I need to do is remove that isolation layer to place the chip so that there's metal on metal contact. So I'm really exposing the metal of my package here so that I can land the chip, so that I can solder the chip to the metal on the package. So I need to add 2 layers to this. Well, really, I need to add a bigger landing pad and a solder mask layer for this to work. So now I'm going to talk about the third spec that we have, which is versatile. It's got to be versatile. So what I can do in this technology down here, if I go to the configuration, options, technology, nested technology. It's kind of like nested, like those Russian dolls where they all nest together. That's why it's called nested technology. I'm actually going to change this to flip chip now. I always want it to be flip chip. And what I'm going to do is I'm going to add in an AEL function. So I wrote a macro function, and believe me, if I can write a function, I'm not a coding guy. So if I can write a function, it's not that difficult. But there's a whole lot of built-in capability behind the scenes here. Also, let me make sure I got that right. Add custom landing pads to RDL. So I wrote this macro function, and this macro function is going to generate those layers on the fly. So it's going to do 2 things. The first thing is when I place this thing down, it's going to make the landing pad bigger. It's going to actually expand out the ball bump, and it's going to make the pad bigger, and then it's going to draw the solder mask layer too at the same time. So this is all going to happening on the fly in instantiation. So take my bumps, place it down here. All of a sudden, you see these 2 layers appear. I didn't draw those layers just now. This is the landing pad layer. So here's the actual pin, right, the ball connection. Now it expands out. It draws the layer in the technology that I'm putting it in, and then it blows out even further, and it puts the solder mask opening on there automatically. So these layers are generated by the thing that I'm instantiating in the other technology. And the cool thing about it is, if I was to take this and like export, if I wanted to make manufacturing, artwork from this. So I'm going to take this. Maybe I want to go for this type of technology. I'd probably use a Gerber, maybe an ODB++ file. So I'm going to go generate that file. And the really cool thing about it is, the layers that we're making with our chips, we're making these things on the fly. Let me get rid of some of the middle ones here. Those layers appear in the output, the manufacturing. You can see, this is the solder mask layer, and then this is the metal layer. So these will get output to manufacturing, even though they're being generated by the technology that you're inserting into your design. So that covers, let's see, simple, powerful, versatile. I think the other one is scalable. Scalable is pretty straightforward. If you're working in deep submicron nanometer types of processes, you'll know a lot of times what you actually, the things that you draw with the metal are not what gets physically created. So there's some scale factors that take place in the mask. So I'll go remove this thing. Those scale factors are usually not hugely dramatic, but options, technology. But it can, of course, matter. If you want to do EM simulation and you have a drawing on in your tool, right, in your layout, and it's, there's a pad and it's 80 by 80, and actually that's not the same. It's actually 70 by 70. When you do that, then the EM result can be off by quite a bit. So here you can apply a nested technology scale factor. I'm going to make this really big. This is a technology scale factor of 50%. This is not something that I think you'd see in a normal process, but just to kind of illustrate to you. So now I apply that scale factor, and I can take this thing and drop it in, and you can see now it's much smaller. So that scale factor can be applied to account for some of the process changes where what you're drawing in your tool is not exactly what you get from your mask. So that covers the assembly. That was kind of a quick demo. Hopefully it's clear. There's a lot that goes on, and there's all kinds of things that we can also do. We can change, like I've seen people change octagonal pads into circular landing pads. So there's a lot of flexibility in there. But if you just want to stack the two technologies together, it's not that complicated. So now I'm going to move on to our example, which is more realistic case. And I'm actually going to use some of the techniques that I showed you in the easy demo. So this is a silicon chip. This is designed in Cadence, and this is actually an interoperable design kit here. So I can use, I'm just opening the design directly because I can use the open access database and read that in the tool. So we've got to be able to read lots. That's one big challenge. We have to be able to read technologies from different places and different databases if you want to assemble things. So that's one of the strengths that we've got in ADS. And what I'm going to do here, in this case, I don't want to simulate everything. I'm really looking for, just as a designer, maybe a 2-minute or 5-minute simulation of an interconnect. So I'm going to start at the pads here. So I'll start at the pad ring. So essentially what I'm going to do, I'm going to grab the pad ring, cell. There's a whole bunch of cells in this thing, and I'm going to push into that. So now I've got the pad ring that contains some diodes. I've actually separated out the metal from the diodes. I don't want to include the metal into my EMs, or the diodes in my EM simulation. I really want to start from here. So this is my IC technology. I'm going to start, but I do want to capture the pad parasitic from this. I showed you earlier how the pad parasitic can make a big difference in your design. So in this case, I'm going to configure it for smart mount. Now I'm going to do the same thing that I did earlier. I'll say options technology, nested technology, and I'm looking in this library, and actually it's attached to a PDK. And you can see the PDK is configured. Here it's grayed out, but it says flip chip. So the point I want to make is that you can actually configure your technology in a design kit. In this case, it's configured to be read-only. So perhaps the person who made the design kit wanted to always configure that in the same way, configure that in a predictable manner. And that's why I can't change it. That's completely flexible. There's other libraries that I can change. But in this case, I just wanted to point that out. It's possible to configure this even in a PDK like this, so that when designers use it, it just always flips itself over the way it's supposed to. Okay, great. So the next thing I want to do is, of course, stack this onto a redistribution technology. So the chip, of course, has a certain set of technology or layers here, right? These are normal sort of silicon chip layers. And then the redistribution technology is separate here. I've got just a few layers, and I want to instantiate that on. So how does that work? Well, same thing. I just go find my cell, pad ring. And it's just like hierarchical chip design. If you do chip design, this is really the same thing. This is hierarchical design. I can take this pad ring, put it onto another technology, flip it onto the right layer, and assemble it together. And it's really pretty straightforward thing to do. And when I do a 3D view, you can see there's the IC pads. That's from the PDK of the IC technology. And then these are the redistribution technology layers. Similarly, I want to take this redistribution technology. I'm now going to nest this again. I'm going to put this into a higher level technology. This is fan-in packaging, right? I'm going to take this and I want to put it into fan-out packaging. So I'm going to configure this as bottom mount. And you might notice down here I have the AEL function, add custom landing pads to RDL. That's the same function. I am going to, when I place this into the fan-out technology, I am going to increase the pad sizes for these micro bumps. And I'm also going to draw a solder mask layer. So let's do that. And again, how does this work? Well, here, I'll go to package BT. So now I have my package BT. Let's check it out. So I've got nothing here. How do I start with something like this? Well, one of the things I can do is configure it in the schematic window. So this is like equivalent on package design to having a net list. So here we go. Got the schematic window. I simply go update, and I can place my components down here. Let's start with the ball grid array pins. There we go. There's the ball grid array technology. Here's the chip plus redistribution. Here's an L-band filter. This is a mimic filter in the p-hemp process. I can just put these technologies together. Everything just stacks up normally based on the way that I configured the technology. Okay, so the last step is Neuroelectromagnetic Simulation. So what do we do when everything's together and we just want to basically do an EM analysis of a piece of this? So I routed all this stuff together with my technology. So how do I run an EM simulation? Here I'd go to Tools, RF Pro, and I'm going to start a new RF Pro. So I'll walk you through the basics of the RF Pro. I'm not sure, I think the simulation takes like 2 minutes. I'm not sure I'm going to have time. I'm looking at my clock here. I'm not sure I'm going to have time to completely run the simulation, but I'll try. So when this comes in, the first thing you might notice about it is that you only see the package layer. So we can do an EM simulation on the package. That's because these components have essentially a role, and these are designed as circuits. So really what it's saying is, okay, I'm going to treat the things that aren't the package technology as circuits. So I can change, in this case, like this is the RDL. I can change this to sub-design, or sorry, this is the filter. Sub-design, and I could take this chip plus RDL, and I can, that's a layout role, right? Or that's a sub-design here. So really what I'm doing is I'm pushing into the layout technology, right? And you can change these roles around however you'd like. And what do you do next? Well, the next thing that you may be interested in doing is, in a lot of cases for boards, we have vias, right? So we treat the balls as vias, but they're not actually 3D components. So one of the new capabilities in the tool is the ability to actually go and remove some of these vias from the mesh and replace them with real 3D components. So that's what I can do here. I can basically go in, I'll go to my substrate here. I'm going to find the dielectric, the BT balls, and I can actually remove this. I can take it off the mesh, and I can set it to be invisible. So I'm going to remove that. I'll show you how I would add a 3D solder ball to this thing. So I'd right-click here if I want to make a solder ball. I'd say Create New Solder Ball. And now I have this 3D solder ball component. I can actually just type in the information that I want. I can also go and specify where it is. I know that my pad sizes, my balls are about 280 by 280 on this package, so I can do that. Add that in, and there I've got a solder ball. And I can take the material, the exact same material, which is copper, here. This is copper, and I'm going to move it to my solder ball. So now I made my solder ball the same material that the via was. And of course, from there, I can even go further, and I can right-click and go Create Pattern. I can make a linear pattern, circular pattern off of this, and you can see all the solder balls. These are 3D components that appear in the technology. The next thing I want to do is simulate just pieces of this. So I can do the full EM analysis, but I can make these smaller analyses. I might call this one like PA out. PA out. All right. So instead of simulating everything here, I just want to simulate maybe the nets that are from the power amplifier. I have a background in PA design, so that's what I like to think about. So I'm going to call these PA out. So this is these two are connected through this other technology through a balun. So these are two power amplifier nodes, but they actually create a single net. So it's tracing the connectivity from the output of this through the bond wire, through the pad, through this balun on a filter technology back out and to the other side. So I can take this net and I can make it a signal net. The signal net really specifies 50 ohm termination as opposed to power and ground, which are low value terminations. And I'd move it over here. I can take this net and essentially create ports from it automatically. So I can create ports or what's called component model groups, or I can do nothing. I can basically say, no, I don't want to do anything. I can create ports, and this is automatically going to pick now ports for my design. And I can, from there, I can essentially run an EM simulation. There's multiple options for the simulator. The point I want to make here, and I think I'm looking at my clock, I was going to run the simulation for you. It takes about maybe 4 or 5 minutes, but I think by the time I'll run out of time and I want to do questions. The point I want to make here is we can apply different solvers to this. We could use momentum solvers if it's planar. We can use, probably in this case, we'd want to use FEM. But we're only simulating very quickly. We've been able to assemble the technology and get it to a point where it's ready to do the simulation. And we're only simulating a part of it. We're simulating only this interconnect, but through all of these different technologies. And that's really what's needed to be able to design something as complex as these wafer level packages that I was showing you. So with that, I will stop sharing. I'm going to leave just a little bit of time for questions here. So I want to make sure I take at least 1 or 2 questions. So I think we'll go back to the sharing, and there I am. All right, let me change to the let's see. Closing remarks. This is just a brief summary. Wafer level packaging is powerful, cost-effective way to integrate multiple technologies. There's advantages, there's challenges, just like everything else, and I showed you a new technique to both assemble and do analysis. All right, Carmina, I hope we've got a few minutes for questions.
Okay, so with that, let's go ahead and go. There's a number of questions, and here's a question from Joe, and he asked, how are port grounds and signal grounds handled in these stacks? And that was on slide 30.
Yeah, I didn't get a chance. I wish I could have shown you that a little bit more. I just ran out of time there. Essentially, what you can do is grab the metal. So you can take a reference point. It could just be a 3D point, or it can be like a port, and you can drop a pin on the nearest ground plane. This is called a virtual pin, and you can drop it on the nearest ground plane, and that can traverse across technology. So I could grab a point on the filter chip, and I can drop it down to the metal of the package. And that could be my reference ground if that's the closest ground. So the tool will actually go and find that closest ground. Sorry I didn't get a chance to show you that. I would have liked to.
Yeah, great, thanks. And then here's a question from Andrew. How do you fine-tune 3D models to match actual manufacturing output by an outsourced supplier? For example, material and shape of solder balls.
Yeah, this is a big challenge, especially when you're not the one who's in control of the manufacturing process. The thing I would say about it is you need the ability to look at your modeling. And I would say, well, I could spend a long time answering this question. If there's one piece of advice I could give you, it would be to consider the sensitivities in your design. There's something called design of experiments that you can use and find the things that are sensitive. So it could be that your design is really sensitive to the solder ball geometry. And you could figure that out using some of the things in the tool that I showed today. Or it might be that there's no sensitivity, very low sensitivity to that. And what I find a lot of times when I talk to designers doing this stuff is they spend a lot of time trying to model all this stuff. And a lot of the things they're modeling aren't actually the things that their circuit is sensitive to. So I'd say the first step, if you want to try to match your results, is to first figure out what in your circuit, what in your interconnect is sensitive. And the way you can do that, we can provide some links, but there's the technique called design of experiments I've used. I highly recommend.
Mm-hmm. And let's take this one more question from Michael. Are WLP able to withstand automotive AEC Q100 qualifications? I'm not sure if you were able to answer that one, but.
Yeah, I'm not sure I know the exact answer. The other thing about it is there's lots of different types of packaging. So I would just say, my best advice is check with whatever package manufacturer you're doing. That's obviously a spec. So if you're looking at different packages, that's a must-have. The reliability, for example, for automotive is a must-have on your spec, and that may narrow down the types of packages that you can use. And I'd also mention, I just showed you the fan-in and fan-out packages. There's a whole bunch of, there's substrate-based packages as well. These tend to have a little bit better reliability. So And there's also multiple people in multiple companies doing fan-in and fan-out packages, so they all will have different reliability specs.
Well, Matt, guess what? We're over time. Thanks so much, Matt. We really appreciate
Thank you, Carmina.
it.
Thanks, everyone.
Yeah, absolutely. Thanks again for attending Designing Wafer Level Chip Scale Packaging, brought to you by Keysight Technologies. And visit us at www.keysight.com/find/events for a list of upcoming events. Thanks so much for staying with us. Stay well and be good.